Hello everyone, I'm Aditya Deshmukh, currently pursuing my BTP in quantum simulation and building a quantum simulator using the Rust programming language. Quantum simulators help us build, design, and visualize the quantum state vectors which are manipulated using gates, circuits, and the observation of results verifies these quantum operations. Modern quantum simulators use languages like Python and C++, but there are additional overheads which we try to remove using Rust memory management by eliminating runtime overhead, such as garbage collection and reducing risk of memory errors. In today's world, there are many quantum simulators that are being used, such as Qiskit, which writes its packet in C++, Cirq, which writes its library in Python, and Quest, which is a C-based simulator. Objectives are to build a quantum simulator using Rust language, using the borrowing, ownership, and no garbage collector collection properties in the best case. In till the mid evaluation, I studied the Rust fundamentals, reviewed and researched papers on quantum simulators that gave me optimization technique ideas such as deferred measurements and block partitioning for improved cache utilization. I also built foundational understanding of quantum computing, such as direct notation, tensor products, quantum gates, which were essential for implementing the simulator, circuits, and measurements. I also implemented the state vector initialization and basis state preparation based on user input. That is, I took user inputs and based on that initialized states, I also implemented initialization in all zeros. That is, for an n qubit simulator, I initialized it with 2 power n 0. The methodology I used was mainly of bit manipulation, efficient techniques. My simulator uses big endian representation to accurately map qubit states within the state vector. Each quantum gate is implemented based on its predefined mathematical operation. How it is being implemented theoretically is mapped to its practical implementation. Measurement of the state vector is performed using Born rule, that is the norm square of amplitudes of state vectors, where uh, when a particular state is measured, the other states collapse. Uh, First and foremost, single qubit gates are implemented. Single qubit gates are applied to a single qubit in a state of a state vector. Let's say for 3 qubit state vector, uh, we have to apply a single qubit gate on the second qubit. Let's take an example of 1, 0, 1. Here, this is the second qubit. Since it's a big Indian notation, this is the MSP and this is the LSP. Uh, According to the manipulations done by the single qubit gate chosen, uh, then it is converted to its appropriate output. Such as if we implement an X gate, then the output will be 1, 1, 1. Uh, the single qubit gates that I implemented are H gate. This is sorry, this is the H gate matrix according to which I implemented by first calculating the bit on which the H gate is applied, the index, and the flipped index that is used in implementation. If the bit is 0, as we can see, H on 0 gives get 0 plus get 1 by root 2. And H on get 1 gives get 0 minus get 1 by root 2. And we can see the according implementation over here. And these are the outputs seen on 0 and 1. Sorry. This is the X gate, which can also be referred as classical NOT gate, which just flips the qubit on which the gate is applied. So we extract the flipped index and we update the amplitude of the flipped index. This is an example for 0 and for 1. This is the Z gate that does nothing to get 0 but changes the phase of get 1 to minus get 1. It is also known as phase flip gate. This is the equivalent implementation, and these are the outputs. For get 0, it does not do any change. For get 1, it changes the sign to minus 1, like a phase flip. This is the Y gate, which Since the state vector is a vector complex, that is, it takes place in the complex plane, the y gate updates the uh, complex complex values such as for y on get 0 flips the bit and updates it in the complex region of the state vector, and y on 1 changes the phase, flips the bit and updates in the complex region of the state vector. This is the implementation and the corresponding outputs for 0 and get 1. Now we'll see some rotation gates. Rx gate. It rotates the qubit state around the x-axis by a specified angle. Here the angle specified is pi by 2. So we can see the implementation according to the matrix given and the corresponding outputs for get 0 and get 1. This is for Ry gate that rotates around y-axis for the same angle of theta, and according to the matrix representation, this is the implementation, and these are the outputs for get 0 and get 1. And finally, for Z gate, Rz gate, it rotates around Z axis of the block sphere by a specified angle, the same angle we used earlier, and the implementation is done according to the gate specified here, according to the matrix specified here. Sorry. Now, multi-qubit gates. Multi-qubit gates introduces one more qubit to be involved for the application of gate. Here, a control bit is uh, multi-qubit gates involve control bit, and the controls manipulation is done only when the control bit is 1. The first and foremost gate is C not gate. It flips the target bit only when the control bit is 1. This is the corresponding matrix and its implementation. This is the circuit diagram of control not gate, and this is the example output. E not gate along with H gate is helps us to form a Bell state, which is an important state also used to form entanglement. When C swap gates, it swaps the two target qubits whenever a control qubit is 1. This is the corresponding implementation and the matrix to represent C swap gate. Bell states. Bell states are also known as entangled two-qubit states in which the state of one qubit cannot be described independently of the other. These are the circuit diagrams of Bell state and their corresponding outputs. Bell state is created by first applying H gate on one of the qubits and then using the same qubit as the control bit and the other qubit as a target bit. Similarly, this is the HZ state. This is for three qubit state vector. Bell state was for two qubit state vector. This works in the similar way. I'm sorry, this should be over here. And it also creates an entangled state in which qubits exist in a coherent superposition. This is the example output. Finally, measurement. After creating the final output, we measure each state individually. And traditionally measurement is done in 1024 shots. That is 1024 times a measurement is done to see how many times each state vector appears. It's basically probability of state vector appearing in those 1024 shots. This is the implementation of of measurement, where um, cumulative probability of state vectors existing in those specified states. Uh, the probability is calculated using the Born's rule, and uh, uh, R an integer decimal R is chosen between 0 and 1, and for every choice of R, we get one state, and the other states of the state vector are collapsed. For example, in this GHZ states, we can see that the 522 times get 000 appears and 502 times get 111 appears, and this is the corresponding graph. For verifying the working of a simulator, I have used some known algorithms such as Grover's algorithm, which provides a quadratic speedup for unstructured search by amplifying the amplitude of the target state. For example, here the target state is 10110. So the amplitude of 110 is amplified to 94. Actually, Grover's algorithm provides a solution for a target string x such that f of x is 1 and others are 0. This is the corresponding graph. Normally the brute force will take O of 2 power n time complexity, whereas Grover's algorithm takes only O of 2 power n by 2, that is O of, root 2 power n time complexity. And the algorithm used to verify the quantum simulator is the quantum teleportation. Quantum teleportation enables the transfer of an unknown quantum state from a sender to a receiver using a shared entangled resource such as Bell state, one of the Bell states, and through my quantum simulator, we can see that if get 0 is sent, we receive the get 0 correctly, and if get plus is sent, we receive the get plus correctly measured with correct measurements. This is the corresponding graph. Performance comparison with Qiskit. Qiskit is a widely known quantum simulator, and my proposed simulators performs competitively for smaller qubits such as for 8, 9, 10 to be the number of qubits. My simulator takes lesser time than Qiskit due to lightweight design and efficient memory layout. However, as the system scales, that is, as the number of qubits increase, Qiskit outperforms it due to highly optimized backend with parallelization, vectorized operations, indicating that the performance gap arises from implementation level rather than memory representation. That is, the implementation of Qiskit is done in a much optimized way than my present working simulator, and I hope to improve my simulator to the level of Qiskit through my future work. These are the future work that I'll be focusing on. Parallel state vector updates. I'll explore parallelization techniques to distribute state vector computations across multiple cores, improving execution speed. Integration with Rayon using Rust Rayon library will enable safe and efficient data parallel operations, simplifying parallel implementation while maintaining the performance and thread safety. Noise model for near-term simulation. Info. Support for dynamic circuits and optimized memory representation. I hope to include all these in the future works of my simulator and try to scale the simulator to the level of this.